So today's warm-up says, how does the speed of sound heard by observer A compare to observer B, and how does the frequency compare? You saw images that look just like this whenever we talked about sound, and specifically the Doppler effect last week on Friday. So for the first question, how does the speed of sound compare? Is it different, the speed of the sound traveling through the air from this moving fire truck? Do they hear, does it reach them at different speeds? No. Okay, the speed of any wave is going to depend upon the medium through which it's traveling. And since they're both traveling through the same medium, then they're going to be traveling at the same speed. Now, there is a difference in what they hear, and that's what we talked about last week when we discussed the Doppler effect, is the fact that they hear a different pitch to the sound. And so observer A and observer B don't hear the same thing, but the speed's the same. What's different is the pitch. And you can see that there is obviously a different wavelength of the waves, and therefore a different frequency of those waves as well. Because as the fire truck is making that sound, if it's driving toward the wave it just made, the waves at the front get compressed. And the waves at the back are going to get stretched out, and that's what you see in the image there. So at the front of it, observer B, the waves that observer B hears are closer together. There are more of them per second. That means it has a higher frequency and thus a higher pitch. So observer B would hear a higher pitched sound. Observer A would hear a lower pitched sound. Now I will say this, the actual sound that the fire truck is making is the same. They just perceive it differently because it is a moving sound source, and that's what we talked about with the Doppler effect. Okay, so the frequencies compare. Observer B is going to hear a higher frequency than observer A. Please make sure you have answered the warm-up question for today. This should be your last warm-up question for this unit because we are wrapping it up today. You are going to have a test over waves on Wednesday of this week, and tomorrow you have a CFU. So we're going to go over resonance today. It's the last topic we have to cover, and then we're going to talk about your last RA, your last relevant application of the year. Some of you might have been waiting for that. You're like, I need another RA grade, maybe. All right, so resonance. This is the last new topic. So again, you might want to add this to your notes. Resonance, you can describe it as when one object is vibrating at the same natural frequency of another object, it forces the other second object into vibrational motion. But you're going to get resonance whenever you have something vibrating at its natural frequency, and then those waves can build on each other. And we talked about that with standing waves whenever we discussed those last week, and that's because there is resonance in a standing wave. But this example that you see up here being demonstrated, that hand is striking a tuning fork with a mallet. That tuning fork is going to ring, make kind of a, depending on which tuning fork it is, some pitch. It's going to produce some pitch of sound. And then that sound, those sound waves, propagate outward in all directions. But if you have a second tuning fork nearby, some of those waves are going to strike that tuning fork, and if that tuning fork has the exact same natural resonant frequency, it will start to ring as well, even if you don't touch it. Okay, and so that is an example of resonance that's illustrated up here. It's a very common demonstration. If we have enough time, I may go grab the tuning forks out of the closet and we can take a look at it. But again, this is our last topic. So this is actually a lot easier to see with some demonstrations than it is to talk about because it sounds kind of weird when you look at the definition. So I'm going to show you a few video clips today, and hopefully they play for me. But one of the common demonstrations that people will use to talk about resonance, and you may have seen this before, they did it on Mythbusters, but they will try to shatter a glass with sound. because if you can get that object vibrating at its natural frequency, glass doesn't really like to vibrate. It will eventually shatter if you put it under too much stress. And so that's what they're going to do in this video clip, is look at a glass in its resonant frequency and see if they can make it shatter with just sound.
Shockwaves from a punch can do damage to the human body. Now we're going to time warp at 10,000 frames per second to see how sound waves destroy a glass. Jamie Vendera is famous for using the sound of his voice to destroy wine glasses. They seem to simply explode. But what's happening?
I know the sound waves broke the glass, but I couldn't see how. So I'm going to use our slow motion camera to see what we were missing. Instead of singing, I'm going to use a speaker and a tone generator. I have to find the natural vibrating frequency of the glass. I have to match this tone. That's it.
This is the exact tone to make this particular glass vibrate. When the tone is loud enough, the glass will shatter.
I can feel the glass shaking, but I can't see it. If I add a straw, then it's more obvious.
So what's happening here? The straw gets tossed side to side, but I can't see why.
Let's record it while I crank the volume. Alright, I took 10,000 frames per second, and I took 1 second. If I were to play back this whole video, it would take 8 minutes to get through.
Oh, this is amazing. What felt like the whole goblet vibrating is actually the rim bending back and forth, 337 times a second, the same rate as the sound waves. If I draw in the sound waves, you can see what's happening. One wave comes out of the speaker and pushes the side of the wine glass. The glass bounces back just when another sound wave pushes it again. If the timing or frequency of the sound waves is exactly right, the motion will build until the glass breaks.
Wow. So, as we would expect, the speaker breaks the glass nearest to it. And immediately we see a crack that goes all the way around the whole bottom of the frame. I'm going to play that back again. This is where the initial fracture happens, right nearby the speaker. And in about 3 frames, and this is 3/10,000ths of a second, we see this crack go along the bottom where the glass gets thicker and come right back up to the top where it's thin. So if we follow that a little more, this piece has just fallen off, but it doesn't in some sense even know that it's fallen off from the rest of the glass. All of the glass was shaking at about 300 hertz, 300 vibrations per second. And this piece is still doing that. You can see the corners of the glass still flexing as if they were influenced by the speaker, but the speaker is way too far away now to have that influence on this piece. It just has the leftover inertia. And we see that in all the pieces here, even along the top edge of this glass. This piece of glass is not resonant at that frequency anymore, so it can't get energy from the speaker, and all that we see shaking is the leftover energy from what the speaker gave it in order for it to break.
So, if you thought that glass couldn't bend, think again. Time warping changes the way we see the world because it makes the invisible visible.
All right, so again, I said that's a very common example you'll see for resonance, but making something vibrate at its natural frequency where it can build is what we're talking about here. That's what I said. We saw the same thing with standing waves, and in fact, that's what this video is going to do. It's going to use it's called a Rubens tube. to have a standing wave, and then you can set it on fire, which is what you see here. But he's going to explain resonance in his video clip as well, and then we'll talk about it again.
This video is sponsored by the Great Courses Plus. I made a video a while back called A Better Description of Entropy because I felt that the bog standard description of entropy wasn't great and I thought I could do better. It was a really fun video to make, so I thought it could become a series, and this is the next one, A Better Description of Resonance. The bog standard description of resonance goes something like this. If you ping a wine glass or pluck a guitar string, then the note that you hear is the frequency that that object likes to vibrate at. It's that object's favorite frequency. It's the resonant frequency of that object, and that's resonance. It's okay as a description, but I think I can do better. The best way I've found to describe resonance is using this thing. It's called a Rubens tube. It's a hollow aluminium tube. At one end, it's blocked off with a piece of wood. At the other end, it's blocked off with a rubber membrane. And if I tap that membrane with my finger, then that will send a pulse of pressure through the tube, traveling at the speed of sound. When the pulse reaches this end, some of it gets reflected and it travels back through the tube to here. And then when the pulse gets to here, some of it gets reflected and it travels back in this direction. So when I tap the rubber membrane, a pulse of pressure bounces backwards and forwards inside the tube, getting weaker and weaker and weaker until eventually it fades away to nothing. But what if I repeatedly tap the rubber membrane? So I tap the rubber, the pulse passes through the tube, it bounces off here, it comes back to here. Just as it reaches this side, I tap the membrane again. And now the pulse is even bigger than it was before because I've added to it. So now a larger pulse is traveling through the tube, it bounces back, gets to here. Just when it gets to here, I tap it a third time. And now the pulse is even bigger again. Now if I keep doing that, if I keep tapping the rubber membrane at just the right time, the pulse will get bigger and bigger and bigger. And that's resonance. Resonance is getting the timing just right, getting the frequency just right, so that the energy you put into the system adds to the energy that's already there. That's resonance. So the frequency of taps that I need to get, that's the resonant frequency of the column of air inside this tube. But it's not the only resonant frequency of the column of air. There are infinitely many. So, for example, if I tap at the rubber membrane and a pulse goes into the tube, and then I tap it a second time, so now there are two pulses inside the tube, but they cross over like this. And then the third tap happens when the first tap gets back. Or I could tap the rubber membrane twice, so one goes in, another one goes in there maybe, and then a third one goes in like that. And then the fourth tap doesn't happen until the first one gets back. But I'm still getting the timing just right so that the energy I put in adds to the energy that's already there. It's just that I've waited for a couple of taps to go in first. So what's that like when you've got pulses coming in from this direction and the reflected pulses coming back and they're crossing over each other? It looks like this. So the waves coming from both directions, they cross over each other and they add together. And when you add them together, you get something called a standing wave, where you have nodes and antinodes. The nodes are the points where there's no movement, and the antinodes are the points where there's lots of movement. So how fast do I need to tap this membrane to see the effect? Well, much faster than I can tap with my finger. In fact, it's an audible frequency. So instead of using my finger, I'll attach a speaker to the end, like this. So if I can drive the speaker at the resonating frequency of this tube, then the energy that I put into the system adds to the energy that's already there, and we should hear that as an increase in the amplitude of the sound. We should hear the volume go up. So let's try that. Okay, so this isn't one of the resonating frequencies of the tube. If I just bump up the frequency a little bit. Okay, so the volume went up. I found the resonating frequency of this tube. This speaker is tapping the rubber membrane at just the right speed so that the next tap of the speaker is meeting one of the returning pulses from this end. And we're adding to the energy that's already in the system. That's resonance. The problem is, you can't really see what's happening because it's happening inside the tube and air is invisible, which is why the Rubens tube is designed to be set on fire. Before I set anything on fire, I've actually switched out the Rubens tube. The first one I showed you was one I built myself, and it was a while ago, and I didn't know what I was doing, and it's a little bit worse for wear, so I wasn't comfortable setting that one on fire. This is one that I bought. The only problem with this one is that the speaker assembly is completely enclosed, and I really wanted to show you the rubber membrane and the whole tapping thing. With this one, I'm comfortable to set it on fire. So we pump in butane through here, and then we set light to it. The first thing you have to do is fill the tube with butane. Basically, you have to get past 15% butane because that's a dangerous mixture. It's a stoichiometric ratio and it's explosive. So we just have to make sure, again, I can smell percentages. So
I think he's funny. There's your standing wave in fire. You can see nodes and antinodes.
So hopefully you can see the result of the standing wave in the flames. So these points are the nodes, here and here. These are the antinodes. So these points, the nodes where the flames are small, those are the points where the pressure isn't varying very much at that point. The tall flames, those are the antinodes, those are the points where the pressure is varying a lot at that point. And let's see if we can find some higher ones. I swept through a few there. Let's see what we've got.
So you can see nothing happens until he hits one of the resonant frequencies, which is when you hit the standing wave. All right, so I'm just going to stop it here because he's got quite a bit left in there. But it's the same idea with this tube of column of air. He also talks about it with a stringed instrument as well. You can watch the rest of the video if you want. There's 5 more minutes in this video clip. But again, you can see that resonance and the result of that resonance being that standing wave that you get. And we've talked about those before, so. It doesn't have to be music though. Okay, you can also see standing waves in anything really, because everything has a resonant frequency, including the desk that you're, have your computer on top of or writing on, and the building that we're in. And so this clip is showing how that resonance, if you meet the resonant frequency of a building, the building will sway, and that has happened in some earthquakes and the ways that they have started to design buildings a little bit differently, at least in areas where there are more earthquakes, in order to handle that resonance.
Earthquakes have always been a terrifying phenomenon, and they've become more deadly as our cities have grown, with collapsing buildings posing one of the largest risks. Why do buildings collapse in an earthquake? And how can it be prevented? If you've watched a lot of disaster films, you might have the idea that building collapse is caused directly by the ground beneath them shaking violently or even splitting apart. But that's not really how it works. For one thing, most buildings are not located right on a fault line, and the shifting tectonic plates go much deeper than building foundations. So what's actually going on? In fact, the reality of earthquakes and their effect on buildings is a bit more complicated. To make sense of it, architects and engineers use models, like a two-dimensional array of lines representing columns and beams, or a single-line lollipop with circles representing the building's mass. Even when simplified to this degree, These models can be quite useful, as predicting a building's response to an earthquake is primarily a matter of physics. Most collapses that occur during earthquakes aren't actually caused by the earthquake itself. Instead, when the ground moves beneath a building, it displaces the foundation and lower levels, sending shock waves through the rest of the structure and causing it to vibrate back and forth. The strength of this oscillation depends on two main factors: the building's mass, which is concentrated at the bottom, and its stiffness, which is the force required to cause a certain amount of displacement. Along with the building's material type and the shape of its columns, stiffness is largely a matter of height. Shorter buildings tend to be stiffer and shift less, while taller buildings are more flexible. You might think that the solution is to build shorter buildings so that they shift as little as possible. But the 1985 Mexico City earthquake is a good example of why that's not the case. During the quake, many buildings between 6 and 15 stories tall collapsed. What's strange is that while shorter buildings nearby did keep standing, buildings taller than 15 stories were also less damaged, and the mid-sized buildings that collapsed were observed shaking far more violently than the earthquake itself. How is that possible? The answer has to do with something known as natural frequency. In an oscillating system, the frequency is how many back and forth movement cycles occur within a second. This is the inverse of the period, which is how many seconds it takes to complete one cycle. And a building's natural frequency, determined by its mass and stiffness, is the frequency that its vibrations will tend to cluster around. Increasing a building's mass slows down the rate at which it naturally vibrates, while increasing stiffness makes it vibrate faster. So in the equation representing their relationship, stiffness and natural frequency are proportional to one another, while mass and natural frequency are inversely proportional. What happened in Mexico City was an effect called resonance, where the frequency of the earthquake's seismic waves happened to match the natural frequency of the mid-sized buildings. Like a well-timed push on a swing set, each additional seismic wave amplified the building's vibration in its current direction, causing it to swing even further back, and so on, eventually reaching a far greater extent than the initial displacement. Today, engineers work with geologists and seismologists to predict the frequency of earthquake motions at building sites in order to prevent resonance-induced collapses, taking into account factors such as soil type and fault type, as well as data from previous quakes. Low frequencies of motion will cause more damage to taller and more flexible buildings, while high frequencies of motion pose more threat to structures that are shorter and stiffer. Engineers have also devised ways to absorb shocks and limit deformation using innovative systems. Base isolation uses flexible layers to isolate the foundation's displacement from the rest of the building, while tuned mass damper systems cancel out resonance by oscillating out of phase with the natural frequency to reduce vibrations. In the end, it's not the sturdiest buildings that will remain standing, but the smartest ones.
So again, it is not just with music, although most of the examples we looked at with standing waves and resonance are going to be related somewhat to music, but you can see it with the buildings as well, and the same idea of that resonant frequency. Another common example, and they mentioned it in that video clip, was pushing someone on a swing set and matching that existing energy whenever you time it right. So anyway, but for that's it for this unit that wraps up resonance, but you can look at those clips some more if you want. But before we leave class today, we do need to talk about your last RA of the year. Okay, so we are going to be doing a video review project RA. So today, your task is going to be to figure out who you want to work with. I'm going to suggest 2 to 3 people in a group. In fact, you can't have more than 3. But I did have some people in the past that wanted to work alone, and if that is something you want to do, as long as you can figure out a way to make that work with whatever it is you're planning to do. But you're going to be picking a topic. So there's going to be a list of video topics, and I'll show you what that looks like in just a second. And then you're going to figure out who you're going to work with and maybe start brainstorming kind of the most important points from that topic. And then you're going to be turning in a video outline later on, not until May 10th. And then you can work independently outside of class. As soon as you have your topic picked, you can start doing that. The due date for the project is May 20th by the end of the day. The idea is that we are getting ready for final exams and for TEKS, and so we're trying to review the semester, and so we're looking at creating videos to review information so that we can all watch each other's and remember some of the stuff we haven't seen in a while. And obviously you're going to hopefully feel like an expert with one of those topics, even if it was a long time ago, once you've done this. So you are going to have class time as well to work on this. However, I will say this, it is a video, so filming it in class, depending on what type of video you're doing, may or may not be the best option for you. If you're doing like a voiceover, you'll be good, but otherwise, like, you know, after the fact, if you're just trying to film something and then you're going to talk over it later when you're home where it's quiet, otherwise everybody's in the same space, so you might hear each other in your videos. If that's okay with you, then, you know, whatever. But you're going to have class time. I've got dates up here, but you can see it on the calendar as well if you've looked at it. Your grade will be determined by your adherence to the criteria outlined in the rubric, which is in Schoology, so I'll show you that in a second. But you're going to get 30 points for the planning portion of it, 60 points for the video portion, and the video is going to be scored based on whether or not you meet the criteria, and then basically how the quality of your video that you do turn in. You know, can I understand what you're saying? Is it too quiet or too loud? Is the information correct? And those types of things obviously are going to contribute to your grade. And then teamwork, if you're working as a team, up to 10 points for, you know, your participation. So you should be working on it together, but you will be kind of assessing your teammates. We may have bonus points available for the best video. We will see. I don't know. We'll look at that later on. So here are some examples from past years. This student did an animation and worked by herself because that's what she wanted to do. And this would be easy to do in class. She drew everything and cut it out and filmed it.
And at any moment, you may be walking across a soft carpet and reach for the doorknob when suddenly, to understand electrostatics, we first need to know a bit about the nature of matter. All matter is made of atoms that consist of three types of smaller particles: negatively charged electrons, positively charged protons, and neutral neutrons.
So we don't have to watch the whole thing. I just wanted to show you an example. So if you like to draw, that would be an easy one to do in class because you could draw it, film it, and then do voiceover at home where it's quiet. This is another one where he's kind of drawing as he talks.
It's best to think about the direction that heat is moving. Let me show you what I mean. Let's use this red arrow here to show the direction that heat moves. Okay? So here I have this solid ice, and when I want to turn it into water, I've got to put heat into it. Okay? So here these arrows show heat going in. Maybe this heat is from a stove.
Okay, so again, I'm not going to show you all of the videos. I'm just giving you an idea of different types of videos. So animation is one. You can demonstrate something.
If I have two glasses filled with water, and I place a quarter in one glass, the quarter sinks.
Some of these are from chemistry class. This one was over density. She did calculations and stuff too.
It's because of density.
You can do a music video. This is one of my coworkers had all of his students had to do music videos that year. That's what he decided. I'm not going to make you all do music videos, but this is for gravity or universal law of gravitation.
Hold it down, hey, hold it down, hold it down, keep this on the ground. Hold it down, hold it down, hold it down, yeah, hold it down. Not 20 minutes per second, yeah. But she ain't gonna teach the lesson, yeah. Hope you know the odds are dancing, yeah. Gravity about Alexia, yeah. I'ma teach you no cost and cheat. Cause I'm ass, I hope you know what I mean. And divided by distance square. Turn it up, you know, keeping it clean.
So if you're musically inclined, then by all means. You'll notice they did put words at the bottom, which was helpful because they're singing kind of fast at different points of it. So if you are doing something where it might be hard to understand what you're saying, subtitles would be a good idea. But you can do a music video. You can do a skit. Let's see if this plays.
Hey guys, welcome to Bryce's epic skate video. And today we're gonna be shredding up this park.
A lot of them put music in there, and for some reason, this one has the Barney song. So I'm gonna skip ahead.
Impulse can be used. Victory in 2018. Let's slow this deck down. And as we can clearly see, it didn't do anything to stop the egg. And next we'll see how my grandma's old pillow saves the egg. It's alive. Next what we did is we filled the box with...
So anyway.
Remaining constant had the ability to broken glass. Of the
he ends up like taping pillows to himself in order to skateboard.
Thanks, physics.
So anyway, you can do a skit. That's the one skit. Sorry, I'm not trying to watch it again. Here's another skit.
So, speak of the devil. Matters are split up into poles.
They're pretty cheesy, both the skits are.
In the south. When you bring a north and a south together, they attract. But when you bring a north and a north together, they repel. As you can see, the magnets won't stick to each other. Pretty amazing stuff, huh? And to show repulsion and attraction, we draw magnetic field lines which go from north to south. Confused yet? Well, let's look at this human interaction and see what we can get out of it. The only thing that really matters in this ever-changing world.
They chose to do this. I'm just going to say this was not my idea.
This man is simply repulsive. Nothing attractive about him at all. And it looks like she has a similar feeling because she is repulsed.
Anyway, they're talking about magnetic attraction and repulsion.
Anti-game.
So, skits are okay. Cheesy's fine. Okay. All right, so that is just some ideas. If you take a look in Schoology, let me go ahead and open that. You do have a CFU tomorrow, by the way. Your test is not Thursday. I need to change that. That's on Wednesday. But if you take a look in Schoology, the very bottom, there is something that says Physics Video RA Project. And it has information in here, including a link to the information sheet that has the rubric and some other details. It also has a list of topics. Now the actual sign up, if this thing decides to load today, the actual sign up through Sign Up Genius. So let's see, I think this is it. Let's see if I can get it to pull up here because this one, okay, well there it goes. Sorry guys, my computer's been really slow. But you're gonna get a Sign Up Genius link, and you can, that link is gonna come probably at the end of the school day because it is first come, first served in terms of the topics. Since I have 3 different classes at 3 different times during the day, I'm gonna send like a remind out. So if you don't have remind, you should already be in there if you've gotten them this year. But just pay attention because that's going to come later today. But there's different stuff in it on pages 5 and 6 are the topics. So the semester, really we did free fall last semester, but we talked about it again because it was part of projectile motion, so I included it. So free fall, projectile motion, circular motion, universal law of gravitation, energy, momentum and impulse, electrostatics, circuits, magnetism, waves, and light. Now I know we haven't done light yet, but we will do light before all of those work days for the videos, so you can choose those topics. You're not going to do like all of magnetism. For example, you might be doing just electromagnets Okay, or if you're doing circuits or momentum, you might be doing just a video on elastic collisions. But all these topics are going to come out in the link that's going to come in Remind. I'm also going to post it in Schoology, but like I said, it'll be there at the end of the day. So what I need you to do today before you leave is I need you to figure out who you're going to work with. Again, you can work by yourself, but if you want to work in a group, it needs to be either 2 or 3. So you guys need to figure that out before you leave today, because only one person from your group needs to sign up. Please don't have everybody sign up for a different topic. You're going to be working together. Pick a topic you're working on together. So you guys need to have that discussion with whoever it is you want to work with. Figure that out. And then y'all can talk about maybe like what your top 3 choices are from this list. And again, you can get this list in Schoology. Just click this link to open the project information sheet, and you can take a look at what you might be interested in doing. So again, I'm going to give you guys the rest of the period to have those discussions. Again, you can't sign up yet, but it will be sent to you later today. You also need to talk about who's signing up, or exchange phone numbers or something, whatever you guys need to do, make a group chat. But go ahead and get to looking at that. And then again, don't forget you do have a CFU tomorrow and you do have a test on Wednesday.